Yo guys, what's going on? We're back at it, a couple of hours ahead. And yeah, so now we're going to be implementing the mutation part of this. And the mutation part of this is where the actual learning and things will start happening. So this is quite a good moment. This is like one of the most important videos right here. So please pay attention and we'll get started. So we left off on the neat genetic manager. We just took out the print statement that was here, the debug.log. Okay, so we got rid of that, and now we're pretty much done for right now in the genetic manager. We are also going to be doing the mutation in the genetic manager, but we're going to do the mutation after it's implemented. Okay, so after we write the code for it. So right now we can X out of these any open code we have, and we can open up the neat genome code. Alright, so it's been a while since we've been in this in the neat genome, so it's nice to be back. And the mutation is actually not that difficult to do because of how we have the neat genome set up. In each genome class, we have the list of node genes and the list of con genes. For one of the mutations, all we have to do is add a connection. Okay, and then for another one, node genes is going to be a little bit more logic, but either way, all the mutations will happen in the genome because the genome is the thing that actually ends up getting changed. You know, the human DNA is the thing that's getting mutated, and then the human is built off the DNA. So we're following those same principles in code. Our neat genome creates our is a thing that gets mutated, and that creates our brain, which and then our brain is placed in our bodies, so in our fish objects. So give me 1 second, guys. All right, so now we're going to start getting the function set up. So to start off, we're going to add a overall mutation function, and then we're going to add mutations in that function, and it'll be more clear when we write it. So we're going to go public void mutate genome, and this is public because this is the overall function we're going to use for the mutation. This is the function that holds our chances for mutation and all that. So, and when I say chances, the first thing your guys' mind should go to is randomness. This is the function that holds our the random values and all that. So what we'll do is float create. We have two different types of mutations. Before we start writing things in the mutate genome function, let's go to our project and let's see what type of mutations can occur. So we have a mutate to add a connection, and we have a mutation to add the node. The mutation to add connections simply adds a random connection between two nodes, okay, making sure that the direction is maintained. So when we have a random node between 3 and 5, the input node will be 3, the output node will be 5. And that if we have a random edge between 3 and 5, the input node of that edge will be 3, and the output node of that edge will be 5. Okay? And that's what happens here. We can see at 7 is from 3 to 5. Okay? Now the add node is a little bit more complicated, because let's say we have this edge right here from 3 to 4, which is edge 3, right? To add a node, what we end up to add a node, what we end up doing is disabling this edge. So now this edge is disabled, and then we end up adding two edges and a node between that. Okay? And another thing that's important in neat is that we maintain the weight for this edge right here. So whatever weight was on this edge that we disabled gets copied over to one of these edges, and the other edge stays as 1. And that way, there's not too much variance added when we create nodes, right? But that's all explained in the paper, so I hope you guys just, skim over it. You guys don't even have to read it all, but skim over it. It's a good read. But yeah, so if we just have every time we add a node, we just add random edges, it'll just start adding a little bit too much chaos into our network. And anytime we do have like a really good network, when we add a node, we might lose some of the solution. Our fitness might start going backwards. So we don't want that, and this way we really minimize any variance. And that allows our training to actually start changing the edges instead of just our mutation. Okay, so yep. So we're gonna have to do 2 functions, and those 2 functions will be called on chance. There's a chance for creation of edges, and there's a chance for creation of nodes. So we have a float that's edge create edge chance, which we keep at 80f. And then we have a float create node chance, which we keep at 8f. Alright, so the create S chance is a lot higher than the create node chance, because we want the before a node is created, we want enough edges to be put into the graph, and enough of the current search space to be able to be looked through before we create a node to increase the search space. So we'll do that, and now we add the random chance, which is float chance edge. Okay, so the reason why I have these names kind of similar is because I want to emphasize that these 2 are connected. Okay, so chance edge and create edge chance, those 2 are completely connected. Random dot range, and this goes from 0f to 100f. There we go. So we'll get a chance for edge to be created. We'll get a random number between 0 and 100f. And if that random number is less than 80, then we mutate. We add an edge. If that random number is greater than 80, then we don't do it. So that simulates like a 80% chance of things happening. And now let's do the same thing for the node. Chance node will be random dot range. Same thing, 0f to 100f. Right. So in this, we get our mutation chances, basically. Next, we want to do if statements to start creating the to do the check for whether the chance is higher than the create edge. So see if our random chance is higher than the create edge chance that we have over there. So chance node, if chance node is less than or equal to create node chance, then we create a new node somewhere, a new hidden node somewhere in the structure. Alright, and then if our chance node, if our chance edge is less than or equal to create edge chance, then we do the code for create random new edge. Okay. And edge and connection, I know this technically should be connection when I say edge, if you want to really be very, very particular about the naming. However, connection and edge, I think we know what both of those things are. So I don't think there's too much of a problem with this naming. All right. So now that we have, so this will do the mutation for the nodes by creating a node. This will do the mutation for the edges by creating an edge. But then we also need a way to mutate the weights. Okay, which is done. So we're mutating our weights every time the mutate genome is called. But so that's why we don't have a chance for it. So now let's create the three functions we need. So we need a function for create random node, we need a function for create new edge, and then we need a function for mutate weights. Alright, we're going to start with the mutate weights because, actually no, let's start with the create edge because Alright, we'll start with the weights. It's fine. Because then once we get the weights out of the way, the edge and the node will be a little bit easier to do. And so let's get started. Now right after the mutate genome, we will create a new function and call it private void mutate weights. Mutate weights. There we go. And in this, we're going to do something similar to up here. So mutate weights is going to be called every time. Let's go ahead and put that in. However, within mutate weights, we're going to have the chances for the mutation of the weight. Okay, so these are the chances for the mutation of the structure, the topology of the neural network. And over here, we'll have the chances for the augmentation of the weights of the neural network. So the training on the edges. So this changes structure. This changes weights. Alright. So we're going to do something similar where we have a chance and then a random chance, right? So we have a we will have two different things happening, all right? Two different chances. We're going to have a random weight chance, and we're going to have a perturb weight chance. I hope it's called perturb, because that's what I'm going to be calling it. But so we're going to have those. We're going to have those two weight chances. The random weight chance is basically going to pick a random weight, and it's going to mutate it. Okay, so it's going to pick a random weight and slightly add or subtract a value, a random value from it, within a random value from within a range. Okay, and then the perturb weight chance will go through every single edge and randomly add or subtract a random value from that within a range. So the perturb weight chance will go through every single edge, will loop through every single edge, and add or subtract a random number from every single weight of each edge. Okay, that random number is gotten from within a range. Okay, I believe it's perturb. Yeah. Apologies about my pronunciation. And it's equal. So for the perturbation of weight, we want to do it perturb. For that, we want to have a 90% chance because we want that to happen every single time. Alright, we want the networks that do get mutated, we at least want their weights to be getting closer and closer to something that is useful. There's no point in having very, very low values for mutations because then it's going to take us very, very long for training. The lower the value, the longer training will take. But if we get a value that's too high, we might over mutate and then lose solutions very fast. So now after the perturb weight chance, we create a random weight chance, which is 30th, right? And now we create our random ranges. So for that, we do float chance random equals random dot, oh, that's not good, random I hate it when this thing does that. Alright, so we'll do random dot range, and we'll have that range between 0f and 100f, just like above. Same thing again, chance, but this time it's chance perturb, and we'll do that equal to random dot range. Oh my god. Random dot range 0f to 100f. There we go. So now that's done, just like above, we create the functions that will do these things that we need done. Chance random needs to be less than or equal to random weight chance. And then we have another if for chance perturb less than equal to chance perturb. Perfect. And then while above we call the mutate weights, this is the end right here. We don't have to call anything after we call the two functions within this. Alright, so for our mutate weights, we have to create two functions for the one for the random weight chance, for the randomization of the weight, the randomization of a single weight, and then another function for the perturbation of the group of weights. Excuse me. So let's create those functions, okay? So right now we still have four functions to create. We still need to create the functions for these two, and we have to create the functions for this right here. So right here we'll do we'll just write some comments for randomize single weight and perturb group of weights. Okay, so let's create the functions. We'll do with the we'll start with the randomized weight. Call it randomized single weight. Randomized single weight. And in this function, we will simply get a random weight and randomize it. We do that by having an if statement to first see if the connection genes are empty or not. Let me make sure I'll call the con genes in here. Okay. Con genes.count does not equal 0, because we don't. If the con genes are empty, then there's no weight to randomize. So then it will get an error. But now we have an if statement to make sure that doesn't happen, and in the if statement now we have to get a random we have to get an index for the one of the we have to get an index that represents like a random position in the connection genes list. Okay, so random weight equals random. Oh my god. random dot range 0f to 100f. Oh, nope. It's going to be, because I got too used to typing that. It's going to be random range, but it's going to be going from 0, not 0f, because we need. It's going to. This represents a index, so it's going to be an integer. So from 0 to congene dot count. All right. So we will get a random number between the 0 and the congenes that count. If congenes is 0, then we'll get 0. I mean, but we can never, congenes can never be 0, because this is right here. If congenes is 1, we'll get 0. Okay, and then if congenes is 2, we'll get 0 or 1. Yeah, so we're within the index. And then next, now that we have the random index, we want to create a reference to the congene thing is going to get me. Create a reference to the connection gene. And so now we get the from the list of congenes, we are just getting a reference to the object that's stored within the random weight index. Okay. We'll change the name from random weight to random con index, and we'll copy that and paste that where it should be. So this is how your code should look in this section right now. Okay, please remember to change those two, because if you don't in the future, when I reference it, it's just going to be hard to make sure everything is lining up. All right, so now that we have that, we're going to call connection dot weight equal to, excuse me, connection dot weight equal to random dot. So there's two ways we could do or the randomization of the single weight. We can actually perturb a single weight instead of doing a whole group, right? Or we can simply reset a weight within a range that we give it, a random range. So reset the let's say we're perturbing, and one edge keeps on getting subtracted from, right? And it goes down to -5 or something. That's a little bit too much of a negative number. So if we have a random chance of getting edges back within range, that might help get that number right back to where it should be. Okay, there's a chance for that. There's going to be a chance for weights that are too far out of range that are making networks work bad to get reset, and that will help the network maybe in the next generation have a better fitness. Okay, so we'll actually instead of perturbing a single weight, instead of randomizing a single weight by perturbing it, we're going to simply set it to a random dot range. Well, -1f to 1f. Alright, so then we set it back within our range. Alright, so that's looking good for the randomization of a single weight. So right here, it gets randomized, everything is looking good, and that function is done. We can go ahead and add that function. Save that, and now this part is done. Next, we're going to add the function for the perturbation of the group. And this actually is not that hard at all. We're going to call it perturb weights. And in this is going to be a for each. Congene. So what we're going to, for each congene in the congene list, in congenes, we want to now grab the weight of the con and simply add and subtract a random value from it. So we will do con.weight equals con.weight plus, I'm gonna add parentheses right here, random dot range, and that range will be from negative 0.5 f to 0.5 f. Alright, and then we're also going to multiply that by 0.5 f. Okay, so this is something you guys don't have to do. Right here, you guys can make this value very small, change it to like 0.25, 0.25, so negative 0.25 to 0.25. But I like to have it multiplied by a constant that scales the value of whatever range I get. So I can make this lower or higher on the fly really quickly instead of having to change both of these and making sure they're like lining up within something. Okay, so this is the value that we're going to be adding to the con weight whenever we do a perturb. Okay, and we can make this value bigger or smaller, but from my testing, this value has worked, so I'm going to leave it as that. So the perturb weight function is now done, which it was a very simple function. Save that. Now we're going to, before I write the other two functions for the create random node and the create new edge, I'm going to first look at the editor to see if we have any errors. Awesome, not bad at all, not bad at all. Alright, let's get back to it then. Now let's create the function for the creation of node and the creation of edges. Starting with the creation of edges. So this is where kind of all the magic is happening in this. So we have to make sure we make the function correctly. We have to make sure both of these functions are keeping the edge, keeping the flow of the edges lined up. So when we do a feed forward loop, nothing is flowing in the wrong direction. Input is not connecting to output, something like that. Alright, so like if we have an input node being like 3 and an output node being 5, that works out fine. But if we have the input node being 5 and an output node being 3, well then we're going backwards. So well, whatever the case, let's get started on making this, and you guys will see what I'm talking about when we get to that part of the code. So we're gonna name this function add random connection, and for this, I need some more water. For this, starting off, we're going to have to grab two random nodes, right? Because when we create an edge, realistically, we're creating an edge between two nodes. All right, two random nodes. So that's going to be our first step. We get a first node that is between a random. I hate that. Wow. So our first node is going to be, we're going to get it from a random.range. So it's between 0 and nodegenes dot count. So we're going to get an index for the first node, and we're going to get it from the node genes. And then afterwards, we're going to get the second node. And there we go. So we get two nodes, and both of them, we get them from the node genes. Okay. Excuse me, guys. I'll be right back. I'm sorry, my brother just walked in. So let's continue this. So we get the first node and we get the second node. Now we need to make sure. Well, we get the first node and the second node. Now we also need to store the types of the nodes. Like, what node did we get? What is the first node and what is the second node? So we do that through this. We're going to create a variable for node gene dot type of type type, and we're gonna call this first type. We're gonna equal this to node genes. We go to the index. All right. So we get the type of the first node. So we get the first node from a random.range, and then now we get the type of that first node because we have the index of the first node, and that node is stored in the node genes object. So we have the node genes list, the node genes array, and then we give it the index that we got, the random index. So that's the first type, and the second type is node gene dot type second type equals node genes second type dot type. The reason why we're getting the types and storing them is because we want to be able to know if the first node, the second node is input node, output node, or hidden node. And once we know that, we can control the flow of how the edges are connected. We know that input node, if input node is connected to output node, we need to switch those. Like if it's in the wrong flow. Or if a hidden node is if the first type is a hidden node and the second type is a input node, we know that's going backwards as well. So another way to do it, however, is just to go off the list. So I'll just go off the index of the list. The lower, if one is higher than the other, if like 3 is higher than 4, then we'll switch them. Or 4 is if the first type is higher than the second type, then we switch them, because we always want the first type to be a lower index than the second type. So that will also keep control of flow. But regardless, we're going to do this method right here, starting with a type, and we're going to do the other one too. Now we have our if statements. So if our first type equals the second type, and our first type is not then we simply run this again. Now this is where the recursive function comes in. Because then, if our first type and their second type are the same, there's no connection that we should make. We should simply rerun this again and get new first types and second types. And if our first type is not a hidden node, again, there's no reason for us to run this again. However, I don't think this is correct. If our first type is going to be, thinking about this, if our first type should be able to be a input node, and our second type should be able to be anything. So first type equals okay. That does make sense, actually. Alright, let me re-explain this now that it makes more sense. If the first type equals the second type, if first type equals the second type, the only time we can allow that is if the first type is a hidden node, right? So if the first type is a hidden node and the second type is a hidden node, then connections between those two nodes can still happen, because 3 might be a hidden node and 5 might be a hidden node, okay? And those two, a connection is allowed. However, if the two types equal each other and the first type equals input node or output node, then that connection is not allowed, because that is interlayer connection, right? No nodes in the input node, no nodes in the input layers should connect to each other, and no nodes in the output layers should connect to each other. And this this if statement makes sure of that. Anytime we do have a case like that, it reruns and tries to get another group of random nodes. So that's what that if statement does. And now we are going to, there's a couple of rough statements here. So we're just going to have to try our best to go along with this. However, obviously everything is I have to make sure all my statements are correct here in the reference code, because there were some errors, and the whole point of creating this code along is to fix those errors. So now we're going to do a for each statement, in which we're going to go through the conjugate. And this function makes sure that we do not have any pre-existing edges. We're not creating any more any duplicate edges. Okay, so we're doing a for each to loop through all the connections in the conjugate array. And for the if statement that we're going to use, we're going to do if first node equals con.id, con.input node, and where's the and the second node equals con.output node. Let's put loops over that. Oh, we'll put this whole statement inside of parentheses right here, and then we're gonna do an or statement then again, or second node equals pon dot input node, and for first node equals pon dot output node. Alright, so if either of these cases happens, we know that we're having a duplicate edge being created, right? So if the first node equals the ID of the connection's input node, and the second node equals the ID of the connection's output node, then we know that these two numbers that we've gotten, the first node and the second node, already have an edge between them, so we don't have to create an edge between them. Okay? And then if this happens, and the same way if the second node is the input node and the first node is the output node. Okay? So that was a long, this was a long one right here. I'm going to slowly just go back and forth over it. So if anybody is trying to, pause the video at the right times, they have all the opportunities to. Alright. But honestly, what I should do is just that. And let's see if there's any errors. Call paths return a value, and that's because this is not returning anything. So if this is the case, we just return false. We simply do not want this to happen. Okay? The reason why we aren't rerunning this function recursively, because there's a chance of endlessly calling recursion on this function if we use this if we do it in this. Because if a connection exists and there's only one connection, that one connection is always going to exist. So this is going to return, it's going to recall itself, and it's again going to get a false, again going to get a false, again going to get a false, and it'll just keep looping for infinity. So that's why over here we simply return false instead of rerunning the function. Alright guys, now let's do the last if statement, the last check that we need to do. And in this check we're going to do if first type is equal to node gene dot type dot output, or if the first type is equal to node gene dot type dot hidden. Where is that? And the second type is equal to node gene. Okay, before I type this, I'm going to click enter right here, tab, and now let's continue our statement. So, and the second type is equal to node gene dot type dot input. Then we simply want to switch the two. Okay. So the first type is equal to the output, and the first type is equal to output, or the first type is equal to type dot hidden, and the second type is equal to input. Then we want to call the function. Right here, I'm going to add more braces just in case. This is one way to do it. However, within hidden nodes, there still will be some edges that are going in the wrong direction, right? And to solve that, another if statement will be needed, but I'm not going to implement that right now because this should be enough for proper training at least. And the genetic algorithm should take care of not having too many edges that are going in the wrong direction, because they simply will not be called. Any edge that's going in the wrong direction will not actually feed any information forward, if that makes sense. Because that information will go backwards, but then it won't go anywhere from there. But our fitness function will get rid of any unnecessary any like very mutated networks. That's why we have the fitness function. So this is good enough for now. Now we will switch these. That's a simple switch. I've already explained why we need a temp, and by switching I mean we're going to switch the first node and the second node. Alright, so the second node is going to equal the first node, and the first node will equal what the second node used to be. And now we want to do the same thing, and now we want to get the type again. So now that everything is switched, we want to make sure we switch the types. Well, we don't have to switch the types using a temp, since we can just reference where they are in the con genes array, or the node genes array. So what I'll actually do, well, I'll just type it out. Alright, so now we have the proper first and second types. Now we can basically create the new edge. Alright. There's also one more thing we have to take into account, and that is the fact that we need to know the next innovation number of each edge. We need to know every innovation number. And so we have to make sure our innovation number is slowly growing from 0 onwards up, and that we're keeping track of that in order, so that when we do the speciation and we do the crossover, we can use the innovation number. So let's do the part of creating the new edge, and then we'll show where the innovation number comes in. Okay, so we'll create a float called weight. Well, we'll call it weight, and we'll equal it to, I'm calling it weight. So we'll have a float called weight, and we're going to do a random dot range. So our random dot range, and it's going to go from -1f to 1f. So we create a new, the weight that we're going to get for the new connection is going to be between -1 and 1f. And we have a bool for the active and that's going to be true. And now that we have that, we can create the connection and create the con gene and call it new con, and have that just initialized. The one problem here we have is that we do not have an innovation number. So our in node is our first node, our out node is our second node, our weight, so we have way right there, call that wait. Our active is act, right? So just the bool act will be passed to active right here. And we still need something for innovation. Okay, so innovation is missing. We will call this enov, and we'll make this for right now a int enov, okay, equal to 0 for now. But we have to create a function and actually get the next enov. Okay, because each of our con genes has an innovation number, we have to just know what the next one is and keep track of what the next one is at all times. So we're going to do this by creating a function called get next innovation number, and that's going to be private int. It's going to be returning an integer. Alright, and that is going to be, we're going to start off by having an int next enov equal to 0, and we do a loop through the connection list, the con genes, and now we do an if statement. So if this number right here is less than whatever innovation number we're looking at, we then want to set the next enov. Then we want to set this number up here to be equal to the con.enov number. So if the connection we're looking at enov number is higher than the current enov number we have, or it's lower than the current enov. I'm sorry, I'm confusing myself with this. If the connection's innovation number is higher than the next innovation number, we then store that next innovation number right here. Okay? And then at the end, we're just going to add 1. We have the biggest. This loop gets the biggest innovation number that we have, and then this adds 1 to it to get the next one. Okay, and then we return next enov, and that is looking good. Let me 1 second see how our time is looking. Oof, we're up there with the time, guys, but we're going through this. We're getting along, so that's fine. Now let's call the next innovation number. So right here where it says int enov, we want to paste get next enov and just call that function. So this will give us the next enov, and that will then get created in the new con. Alright, so this is the new connection that's been created. Now we simply have to add that new connection to the list. Sorry, I haven't slept all night. So, and it's 10 o'clock in the morning. Alright, so con genes dot add new con. Now the new connection is added to our list of connection genes. That looks good, and now we simply have to return true to make sure that code paths are returning something. Okay, and I don't even have to return anything. We can just return false and stuff, but right here it's easier to return false, and right, you know what I mean. And in the future we might use this. In the future we might use a if statement in the mutation. Okay, but for right now, we're not. The bool doesn't matter as much, but just keep it, and yeah, just follow this kind of pattern right here. Again, in the future, we also could change the way we're creating edges, specifically the way we're treating how we regulate where edges are created. Any of that is going to be done right here where I highlighted. So, but for right now, we're going to keep all this just like this because it works, and it works well. So we're going to copy this and paste this where the new edge should be created. And that is our creation of the new edge. Now we have one more function to create. However, within that function, we need to create another function. So technically 2 functions to create. But yeah. So now let's create the... It's also going to be a private bool. And we're going to create the creation of the random node. And this function is not as bad since it's we get an existing node. This function is not as bad because we get an existing edge and simply are splitting that edge apart. So it's not as much regulation of making sure that it's not like making sure that it's not a node that already exists. We know that it's not a node that already exists because we're splitting an edge to create it. But yeah, so we're going to do. But this one, since we don't have to do any of the weird returning and the recursion, we're just going to do a void. So private void add random node, and that's going to be our function for the addition of random nodes. Okay. Now, to begin, like we've done in the add random connection, let's start off by getting a random something. In the random connection, we got 2 random nodes and create a connection between, but in the add random node, we're going to get a random connection. It's funny how those 2 are switched. But, yep. Random con equals random, and we've done this before somewhere, but yeah, here it is again. I'm just going to copy this, paste that, and then range, because my editor keeps auto completing that. So we're going to do random dot range, right? And then this goes from 0 to connect due to con genes dot count. Alright, so now we have a random connection index that corresponds to like a random connection in the connection genes. Now, next we want to get a reference to that connection, right? And we want to get the input and output nodes that connection is connected to. So what we're going to do is con gene mutating con, because this is the connection that is mutating, and that afterwards will be left disabled. So mutating con equals con genes, and now we just get a reference to that random con. So we go to the con genes and we go to the index that will be of random con. So that we got from the random dot range. Next, we're going to get the first node and the second node, starting with the first node. So mutating con dot input node. We're just going to store that. We're going to store and then we're going to store the output node. So we have the input node and the output node lined up with first node and second node. Now that we have the nodes input and output node stored, we can go ahead and disable the mutating node. Our mutating connection, not the mutating, the mutating connection. Dot is active equal to false. So all of them start off by equaling true, and then, when we disable them, they equal false. And because of that, we're going to have to make sure about something in our feed forward loop. We have to make sure we do not feed forward when we have disabled edges. But for right now, we won't look at that. We'll just finish this up. So mutating con is active. It has to, we set that to false because we already have the first node and the second node. So we can go ahead and disable the mutating connection. And now after that, we have to create the sub function that I was talking about. You know how I said that this function, we're gonna have to create another function to finish it. We're gonna have to go ahead and create that. So similar to how in the add random connection function we had to get the next innovation number, in the add random node function we need to get the next node ID. Alright, so we do something very similar to get the next node ID, which is create a function which returns the next node ID. Alright, so we'll create this function. It's going to be a private, and it's going to return int, similar to how the other function did. We'll call this get next node ID. And now in this function we do just very similar to what we did before. So we loop through the node genes list, and we see if any of the IDs, and then we see which one of the IDs is the largest, and we store the largest ID in the next ID variable. And then we have to increment the next ID by 1. And then we can return the next ID. We increment by 1 because we get the largest ID within the node list, right? So we get the largest ID within the node list, but then we have to get the next ID, which is 1 above the largest ID in the node list. One more thing interesting, in the get next node ID function, we loop through the node genes, right? While in the get next enov number function, we loop through the con genes. So just things to keep track of. Alright, so now that we have that, we can go ahead and start with the addition of the new node and the new edges. Because we pretty much have everything we need for the new node. Alright, so we'll call this int next ID equals, actually call this new ID equals get next ID. So we have our new ID. And now we create the new node. Because our constructor just takes the ID. So we pass. Oh, and the type. The type for the gene, any new gene that we mutate is always going to be a hidden gene. We never mutate input nodes or output nodes, because that would be weird. The input nodes and output nodes are dependent on the domain that we're searching. So like, it's dependent on how many sensors the fish has and how many ways it has to move. So turning and moving forward, things like that. And that's all dependent on the problem itself. Alright, so no gene. So the type that we pass it is always going to be hidden. And that's the ooh, I missed the equal sign. Now that's the initialization of the node gene, the new node gene. Now we simply add that to the new node. Okay? Add that to the node genes. We add the new node to the node genes. Now we are going to have to create two edges that connect this to new node to the first node and the second node. Okay, so it's going to be the first node connected to the new node connected to the second node. All right, we do int next num equal to get next num. Okay, and then we create a new connection gene, and we'll call this the first new con. And right here, we pretty much know what we need to set the new con to. Our new con is going to start off, the input node will be the first node. Then the output node will be the new node. Then we're gonna get the weight that was assigned to our mutating connection. Okay, so we don't want to add a random weight in this. We want to use the weight that is already there, so that we don't add too much variance to this network when we mutate it. So we take the weight from the mutating connection, and this is obviously going to start off being true. And then we simply give the next number right here. So we get the next innovation number right up here, and then we pass it into this, and we close the and that's the initialization of our con gene. So we just close it off. All right, now we have to add this to the connection genes list, right? So con genes dot add first new con. Now we're going to create the second new. Oh, before we create the second new con, we want to get the next innovation number. So we just added the con gene, the first con gene, and so now we have to get the next innovation number. So next innov number, and we just call that function again. All right. So we get the next innovation number again. Now we're ready to create the second new connection. And now this is going to the input node for this one, the second con gene. is going to be the new node.id, and the output node will be the second node. All right, and that will complete the connection. And then the weight is going to just be 1f, because when we multiply anything by 1, it's just itself. So we're not going to be this weight is not going to be affecting our network at all, really. And then we pass true for the function, and then we just give it the next number, and that's pretty much good to go. I'm going to, however, change this real quick. I'm going to it says right here where it says mutating con weight up above, I'm going to change this one to 1f, and the bottom one I'll change that to mutating con dot weight. All right, so this is the completed section right here. Just take a look at this and make sure your code is copied over properly. All right, now that this is done, we're going to save this and we're going to see if there are any errors. A lot of errors. All right. Hmm. Let's see what's going on. What's going on? So cannot convert no gene type to int. Where are we converting a type to int? We wrote a lot of code without looking at this, so I'm just going to go over this whole block and comment it out to see if how many errors get fixed, so we know where the errors are. It looks like it's not even in that block of code at all. That's a good thing we know that. Let's go ahead and look around to see where it could be. So now I'm going to comment out everything from the add random connection function as well. Save that, go back to Unity, clear. Now we only have most of our errors are gone. So that is explaining a little bit of what's going on. So somewhere in here we are messing up. Ah, yes. So in this function right here, where we're getting the type, I believe we also need to cast this type. Well, I'm not sure. So what I'm going to do is just first of all, comment everything out in this line and leave our you guys don't have to be doing this. So I'm just debugging through this. You guys can just watch, and then once I find the errors, I'll announce that I found them and you guys can go and change it. But yeah, or you guys can do it, whatever. So I'm going to comment out this line to see how many errors are fixed. Okay, so I do believe the error is somewhere in here. What I'm going to try, just off the top of my head, is no gene dot. I'm going to cast this to no gene dot type. Okay, let's save and see if that. Nope. Cannot convert no gene dot type to integer. Why is it converting it to integer? The only where I can see, where I can maybe even think that something's going wrong is right here. So just to test it, I'm going to copy this, paste this, comment this line out, these two lines out, and change this to no gene dot type dot input, and this to no gene dot type dot output, and see if that changes the error at all. Yep, that solves it. So that's very interesting. Let's go down to 109 real quick. That's very, very interesting. Because this should, let me see something real quick in my reference code. I'm gonna go to the, well, you guys can't see it, so it doesn't matter that much anyways. Yeah, I don't really understand why that would be doing that. If we look over here, we go to the neat genome right here, and in the neat genome, if we go down to the we have a private, it's a public type, right? So when we're accessing that type, we shouldn't have any problems. It's just not really converting an int to the no gene dot type. That's very, very interesting. Okay, I'm going to, when this happens, for some reason, we also do not get errors right here. This one doesn't give us errors. This one does. Ah, I know. All right, good, 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 good. Let's go ahead and go ahead. Wow, right here, I'm passing it second type. It should not say second type. It should be second node. All right, guys. So that's the error. I'm passing it. Oh man, that's horrible. It was second type being indexed, and we cannot index second type because it's type. It's not an integer. So we have to change this to second type. That was one of the errors. Now let's scroll. First node. My God, I did it again. Second node. Change this to second node. So first node, second node. All right. Really sorry about that. And then down here, we also will do second node. And the hint for that was that the error we were getting was on line was on the second line, but not on this line for some reason. So now let's see if that solved at least some of our errors. Apologies, and that was the only error we had. Wow. Okay, that took a minute, but we did find it, so that's perfect. Now let's uncomment all this code. So now that we found the error, we know that it was very simple. It was just changing the second type that was written here to second node, which is the integer it should have been. Okay. So we uncomment the add random node function. saved it, and now we reload the script. So let's load it up, and no errors, so that's looking good too. Now let's simply add that to the random, oh my god, node right here, and that is the end of our mutation genome. We have finally added mutation, guys. Everything is done for this mutation. We add random node, we add random connections, and we mutate the weights. Awesome, you guys. That was great. Let's make sure there's no errors. Apologies for that one blatant error, but it happens sometimes, especially when, you know, you've been up all night and it's almost 11 o'clock in the morning. This is interesting right here. Perturbed weight chance is assigned. Its value is never used. That should not be true. Let's look at the code real quick before we move on. So he said perturb weight chance. So let's, yep, we call chance perturb twice. This is one of those errors that don't show up in the editor. Like, it showed up as a warning. Usually people just ignore that. But it's another one of those blatant errors. Alright, so let's change that to what it should be, which is perturb weight chance. And there you go. Now that is also fixed. I want to make sure chance perturb is less than or equal to perturb weight chance. Yep, that looks good. Now we also are not getting any warnings anymore, which is perfect. Everything has been solved. Our mutation has been done. Our genetic manager is done. Almost everything is done. Now all that's left is to actually mutate in the genetic manager and see the network get closer and closer to solving the problem. So now in the next video, we should actually start seeing the solutions start forming. So we'll actually see some chasing behavior, and that'll be awesome. Alright guys, I can't wait for the next one. Peace out.